Hi everyone, my name is Pradeep Shetty. I'm here to talk about our paper, Building Workload-Independent Storage with VTTrees today. So I would like to thank my co-authors, Rick, Ravikant, Binesh, Justin, and my advisor, Professor Erez, Zadok. We are all from Stony, Brook University. So let me start by talking about what kind of file system we want to optimize, something which keeps the data persistent, otherwise nobody is going to use it. And something which is reliable by providing crash recovery, and something which performs efficiently for workloads like sequential read, sequential write, and random read and random write, and also any mixture of it. So when I talk about sequential read and write, it's basically reading or writing large files like video files or high resolution photos or VM images. For random read and write, it could be a small file, or it could be metadata workload, or even application level metadata like storing MP3 tags for MP3 files. So this could be at a page level or even at a sub-page level. And then an application developer would allow to see a file system which provides low overhead transactions, so it makes their life much easier by having to write less code, resulting in less error and less bug. So in this talk, I'm going to focus mainly on the performance aspect of these 4 workloads we talked about, and also a little bit on transactions. So let's look at how the existing file systems do against these 4 workloads. So in this slide, we're going to focus on the workload for which the corresponding data structure used in an existing file system doesn't do well. So for example, the file systems like ext4, which use extents and block tree, doesn't do well for random write because they use in-place trees, and doing a random write requires disk space or write amplification in case of SSDs. LFS try to solve this random write, but they still suffer for random writes happening at a sub-page level. That's why there is a yellow smiley there. And then a sequential read. So if you write randomly to LFS and then you end up reading sequentially, the sequential read becomes a lot of random reads. There is copy and write, which provides you additional features like snapshot and versioning, but still inherit a similar problem. So VTTree would have issues with a random write requiring disk seeks or resulting in write amplification. And then we have LSM-tree, which is widely used in write-optimized databases like Cassandra, HBase, or Bigtable. They have a very interesting property that they have a good sequential read as well as random writes, but they have problems with sequential write. So we're going to discuss about LSM-tree in the next few slides. So what we did as part of our paper is basically to build a single data structure. We call it as VTTree. It's a novel extension to LSM-tree. It performs comparable or superior to all the 4 workloads we discussed, and it lends itself to an efficient transactional architecture, as well as it is flexible such a way that you can configure VTTree to span the continuum from LSM-tree to LFS. You can dynamically configure VTTree to behave for some workload like an LSM-tree or to LFS or anywhere in between the continuum. So let's try to understand what an LSM-tree is. So a traditional LSM-tree would contain, so basically LSM-tree is widely used for random write workload, and the write size, as I said, could be a sub-page level. Let's call those updates as tuples. So LSM-tree has something called as memtable, which can hold R tuples, and it keeps it sorted. So once you have inserted R tuples, you end up sequentially writing that to an on-disk list called as SS table. And if you keep on inserting more, and after inserting R more tuples, you create another SS table. So you do this until you have, say, K SS table at the same level in the tree, and then once you've done that, we do something called as minor compaction. So the minor compaction basically merges this SS table into one large SS table of size KR using, say, K-way merge sort, resulting in a SS table of size KR tuples. So as you could see, the writes in LSM-tree is basically always sequentially written, and there is no disk sakes or write amplification in this case. So that's good for the write workload. And for this random write workload, these minor compactions actually help to get the data closer on the disk. So making, if you're doing a sequential read later, you'll have a much better performance. So this minor compaction helps the random write workload and then gives you a better sequential read throughput. But the same minor compaction actually causes a problem or acts as an evil for sequential write. Because as you could see, the minor compaction results in merging the SS table and writing into a new list in the hope that it would make it more sequential. If the data is already sequential, you're just simply doing more copies. So it could result in basically log n base k more copies when you compare that to any other traditional file system, which would do at max like 1 corresponding write for a sequential write. So that's the problem we're going to solve here. Just to explain how the lookup works, the lookup needs to look at all the SS table here. So in order to avoid IOs going to all SS table. Each SS table comes with a Bloom filter to avoid negative IOs, and it also has a secondary index, which would basically get you the tuple of interest in one IO. So we solve this problem of sequential write with the LSM-tree by using our data structure called VTTree, and the extension we do here is called stitching. So stitching basically lets you ask the simple question. Basically, what we're trying to do here is optimize the minor compaction, which would do unnecessary copies. So in order to do that, we have something called a stitching, which helps during a minor compaction to avoid unnecessary copies. So stitching basically lets you ask the question, do I really need to merge these tuples when I'm doing minor compaction? And a simple answer is a block of tuples from one SS table, if it doesn't overlap with any other block on the participating SS tables, then we don't need to actually merge them. We can leave it in place, or what we call as we can stitch them. So let's try to understand what stitching with an example here. So we have two SS tables on the disk, SS table 1 and SS table 2, each backed by a zone Z1 and Z2. So zones are basic allocation unit within our system. It's very similar to segment in LFS. And then each SS table 1 and 2 has corresponding secondary indexes, SI1 and SI2 cached in RAM. So as you could see, an SI entry actually points to a block worth of tuple in the SS table. A block here contains only 2 elements. So a second index entry would have the first key and the last key within that block. So in this case, 0 and 1 becomes the key for the actual tuple with the key 0 and 1 on the disk. So let's try to do a minor compaction of these two SS table, 1 and 2 here. So we set the cursor so that we can do a two-way merge sort in this case. So with stitching, we are doing this. So stitching, basically the first question we do is ask is basically 0, 1, and 4, 5, do they overlap? And we know that 0, 1 doesn't overlap with 4, 1, so all we need to do is just copy its secondary index entry. So you could notice that we didn't do any IO, we didn't copy the data during this merge. So the next element is 2, 3, and 4, 5. We ask the same question, 2, 3 doesn't overlap, just copy its secondary index entry. And then it's 6, 8, and 4, 5. The 4, 5 doesn't overlap, so just copy its secondary index entry into a new secondary index entry for the new SS table we're creating. The next tuples we are going to compare is 6, 8, and 7, 9. They clearly overlap. So in this case, we have to merge them. So this requires creating a new secondary index entry for 6, 7, and then copying the data from the existing SS table into a new region. We call it as fill. So 6, 7 has been copied. We updated the secondary index entry. And then we have to write the same thing for 8, 9, copy it into the disk, and then update the secondary index entry. So then we can actually mark or basically the space used by these tuples on the previous SS tables is no longer in use. And then we look at the last element. In this case, 10, 11 doesn't overlap with anything, so we can just copy its secondary index entry. So as you could see, with stitching, minor compaction was fast, isn't it? So stitching helped you avoid block writes. With an LSM-tree, we would have done 6 block writes here. With VTTree and stitching, we did only 2 block writes, and we saved 4 block writes here. Obviously, this doesn't come for free. So as you could see, what it causes is internal fragmentation. Since zone is a basic allocation unit, we have a block worth of data within each zone is being not in use. So the fragmentation is a problem with stitching, so we have to solve it. The immediate way to solve is basically having something called as stitching threshold, where stitching threshold is basically when you're trying to stitch something. In this example, we stitched everything we could. We stitched a single block which doesn't overlap with any other block on the participating SS tables. Instead of doing that, so let's stitch only if there are n contiguous non-overlapping blocks. So if you do that, it reduces the fragmentation. So in this case, if you had taken stitching threshold equal to 2 for the same example, we would have saved copy for the first two tuples, 0, 1, and 2, 3, and the rest we would have had to merge them. So as you could see, it helps you avoid fragmentation, but defeats the purpose of actually avoiding unnecessary copies. So stitching threshold alone doesn't let you avoid the fragmentation, and so we need something to overcome this fragmentation, and we need a defragmentation tool. So let's continue with the same example here from the previous slide, and then we have we did the minor compaction with the stitching threshold 1. So we have zones with utilization only 67%. So the way we actually now defragment is basically find the candidate zone and then move the live data to somewhere else. In order to do that, we give a weight to each of these zones, and the way we calculate weight is basically we want to preserve or improve the sequentiality of the existing data already in the zone. So the way we do it is by introducing a new term called as contiguous span. A contiguous span is a sequence of contiguous blocks which is of at least stitching threshold in length within the zone. So once we know this, we give a score or a weight by which is basically the ratio of total length of contiguous spans within the zone to the number of contiguous spans. This gives you a rough idea about how sequential the data already within the zone, because stitching has done some work to avoid unnecessary copies and keep the data sequential. The last thing we want our defragmentation to do is disrupt that. So we calculate the score. So the score for the zone 1 would be basically 2 because it has one contiguous span of length 2 blocks. And then we have, for zone 2, it's 1 because it has 2 contiguous span of length 1, 4, 5 being 1 and 10, 11 being the other. As you could see, 7, 9 is a dead block there. And score 2 for zone 3. So now we clearly know that we have to select zone 2 for reclamation. And once we find the candidate zone, we do a first fit approach to move the data to any other zones. So what we do first is copy its secondary index entry so that the reads can still happen, and we just modify a new secondary index entry. So we need to copy 4, 5, and 10, 11 from zone 2. So first we go and have 2 cursors, yellow being the 2 and red being from. So we are copying data from 4, 5 block from Z2 to Z1. So we do that copy, update to secondary index entry. And then we know that we have to copy 10, 11, move the 2 to zone 3, and then the from to zone 2 where 10, 11 leaves. So we copy that data. Now the zone 2 is free. We can free them. So this is how we solve fragmentation in our system. As you could see, stitching helps you avoid unnecessary copies, many more than what a defragmentation would end up resulting in a copy, because defragmentation doesn't run as often as minor compactions. So I showed you how VTTree works and how stitching works, and then how we solve the fragmentation issue. So using VTTree, we built a file system, and we call it as KVFS, Key Value File System. KVFS is implemented on top of a key value storage. We call it as KVDB, which is backed by VTTrees. And then in order to support POSIX compliant file system APIs, which we all love, we used a kernel fuse module, and then a library fuse. So then we needed a KVFS layer which would translate these file system operations into a key value operation and forward the request to KVDB. So let's understand this with an example where, say, user process makes a read request. A read request goes to fuse kernel, and in case of not finding the data in the kernel cache, we would forward the request to KVFS layer through fuse library. And KVFS layer would translate this read request into one or more key value lookup into KVDB, and KVDB might find some data in its cache or might need to issue some IO to underlying file system ext4 to fetch the data, and then returns the data to the user process in the same path but in the reverse direction. In addition to providing file system API, our KVFS would also provide, would let the user process to access KVDB directly using socket layer. We do this to support applications which want to store files using file system API and any associated application level metadata. For example, an application wants to store MP3 file and then an MP3 tag. So it can store the MP3 file using the file system API and MP3 tag directly, creating a new dictionary in KVDB and storing the MP3 tag. So in order to make it synchronized, KFS is transactional and lets the application to include both these accesses, like a file system and the key value access, in a single transaction. So, as I said, KFS is implemented on top of a key value storage. So in order to support file system, we have to create a schema with 3 dictionaries in the KVDB. So the 3 dictionaries being nmap to support namespace entries for helping the path resolution. So here, it's very similar to dentry. So given a parent inode number and the path component, you can get the inode number of the file you're looking for. And then imap is being the inode attributes, it's a metadata. So given inode number, it gives you the inode attribute. And then we have another dictionary called dmap to store all the files data blocks. So given an inode number and the block offset, it gives you the corresponding data at that location. So let's look at how this would look at inside KVDB. So we have some, we call this as file system schema. So it has nmap, imap, and dmap. So as you could see, all these are backed by their own VTTrees. So nmap and imap are metadata workload and more random in their nature. So we could configure these two to behave like LSM-tree. And then we have dmap, which could actually configure, we can make use of stitching to optimize it for both random write as well as sequential write. KVDB and KFS both support snapshots. So the way we do snapshot is we have something like an active branch or a default branch. We call it as mainline file system schema. And then in order to take a snapshot, mark it as read-only, and then create a mainline schema with empty VTTrees. And then make a dependency of this mainline schema without a snapshot we just took. This is required because the way all the lookups or all the requests comes to the mainline schema, and then you might not find the data you're looking for because the VTTree are empty in mainline schema. So then we would forward the request to the corresponding snapshot, which the mainline schema depends on. So we might find the data there, and then would return the success along with the data to the user. So KVFS also provides transactions. VTTree being log structured is inherently transactional. We implemented transactions based on snapshots. It can be larger than RAM. Each transaction in KVFS has its own private snapshot backed by VTTree, so where all the write goes. And then, because being log structured and only requiring redo images, we avoid double writes. So that gives us a little more performance. And then KVDB and KFS both expose this transaction begin, transaction commit, and transaction abort APIs to the user to create and commit and abort transactions. We support ACID with two modes of isolation, one being called as snapshot isolation and the other serializability. Serializability is the strongest with no repeatable reads, supporting repeatable reads, no dirty reads, and no lost updates. In this talk, we're going to discuss only about serializability. The more details on snapshot isolation is there in the paper. I would suggest to read it for more details. So let's assume that we already have some snapshots, SSI, we call it as. And then we have an active branch or a default mainline schema. So our user wants to create a transaction, so it would call the transaction begin API, so which would result in creating a private schema with empty VTTrees for the transaction so that all the updates done through the transaction goes there. And then we create the dependency of this transaction with that of the mainline. So now, for example, and then we return the ID to the user so that it can continue to do all the operations in this transaction. Then say assume a process wants to take a snapshot. So that requires to create a new mainline schema with empty trees and mark the previous one as snapshot and read only. So as you could see, the transaction, the dependency is on the new mainline schema, not on the previous one which became a snapshot. So let's assume like another process wants to begin a transaction, the same process repeats. We create a private schema with empty trees, which only transaction can see, and return the ID, and then mark the mainline dependency on the mainline schema. So all the writes done through transaction goes to their private schema, and nobody else can see it. And any writes done by processor which doesn't use transaction goes to the mainline schema. So this transaction always have dependency on the mainline schema, so it would get to see all the latest updates done to any tuple within the system. And then looking at the read, so for a read, say for example, for the transaction T+5, the read first visits its private schema. If it doesn't find it there, then visits its dependency, which is mainline schema, and then any other snapshot that internally depends on. So until we find the data, or basically it returns a no entry, and we have run out of snapshots. So one thing I forgot to say here is basically how do we resolve conflicts. So for serializability mode, we use strict two-phase locking on every access, and we store the lock object within a range tree until the transaction is committed or aborted. So assuming that there is no conflict and the transaction wants to commit, let's see how the transaction commit happens in our system. So we have a transaction ID T+4 which wants to commit. So the way we commit the transaction is basically first we copy the mem table of the VTTrees in the private schema to that of the mainline schema. And once you have done that, we move the SS tables within the VTTree to the corresponding VTTree mainline schema. We move, we don't copy. As you can notice, we place them at the top of the tree so that all the process which is trying to read now gets to see most up-to-date version of the object once the transaction has been committed. So we journal that this transaction has been committed so that on a recovery, you would still find all the updates done through transaction. And then we can free up all the resources associated with this transaction, including the lock objects which this transaction acquired during its lifetime.
So that's about our system. So let's jump into evaluation. We did an extensive evaluation of our system. We used 2 machines with 4 cores and 12 MB L2 cache. We booted the machine with 3 GB RAM. The machine actually has 64 GB of RAM. We booted with 3 GB so that we can show out of cache performance. And then we did the experiment 2 disks, one being SSD, 160 GB SSD, and then the other being a low-end SATA disk. We show that our system has a similar behavior on both the magnetic disk as well as SSD, and then for a single benchmark, and then we continue to do all the benchmark only on SSDs. So the random read throughput of our SSD is being 15 K IOPS, where IO size was 4K. And then random write is 3.5 K IOPS, sequential read being 245 MB per second, and sequential write being 107 MB per second. So the first benchmark we did is to evaluate the effectiveness of our stitching. And in order to do that, we didn't use KVDB layer or we didn't use KFS layer, just VTTree. We created a small mem table so that we can have much more, many minor compactions to show how stitching works. So we created a 8 MB mem table, a small one, and then so the first level SS table would start off with 8 MB. The working set was around 10 gigs of data, so that is 3.3 times the RAM. So the benchmark, micro benchmark we did, we call it as random append. This is neither random nor sequential. It's basically a mixture of that. So the way we did this micro benchmark is to create, have like 2040 files and randomly select one file and append 4 KB to it. So this repeats until we have inserted 10 gigs of data. At the end of this run, basically each file would get on an average 5 MB of worth of data. So we ran this benchmark with 5 configurations with varying stitching threshold to show how insertion throughput varies with the stitching threshold as well as the scan throughput. So the first configuration being no compaction, where basically whenever the mem table is failed, we write it into a new SS table. This is configuration very similar to LFS, where an active segment is failed, you write the active segment into the disk on a new region. And there is no compaction here. So this would get a throughput of around 91.4 MB per second, closer to the sequential write throughput of the disk. And then the other extreme configuration being is setting stitching threshold is large enough that stitching actually doesn't do anything. It always results in minor compaction, very similar to like LSM-tree. So this configuration is basically how an LSM-tree would work for the same workload. So as you could see, LFS gets 91 MB per second and LSM gets 23 MB per second for the same workload. And then we did a stitching threshold of 0 where you stitch everything you could, and this would give us around 57 MB per second. The overhead comes mainly from CPU here, with we having to create quotient filters. VTTree uses quotient filters instead of Bloom filters, and the details on why and what are there in the paper. So the merging quotient filters and creating new secondary index can be CPU intensive. And as I said, we have a small mem table of 8 MB, and you're trying to insert 10 gigs of data would result in hundreds of minor compaction. So this compaction actually has some overhead. With stitching especially is only CPU. And then the other configurations with varying stitching threshold, the one being 16 KB, like 4 blocks, the other being 64 KB, 16 blocks, would give you a throughput between LFS and LSM-tree. So as you could see, with varying stitching threshold, your insertion throughput actually goes down, but this actually bites a scan throughput. So let's see how that looks like. So we have a graph here basically with a x-axis showing the stitching threshold from increasing from 0 to the max, and then a throughput on y-axis, MB per second, higher the better. As you could see, increasing the stitching threshold lowers your insertion throughput, but you would get a better scan throughput at the same time. So the leftmost configuration is being LFS and the rightmost configuration is being the LSM. You could dynamically configure VTTree to get anywhere in between LSM and LFS for particular workloads. So looking at the point query doesn't change much with the stitching threshold because the Bloom filter, or in this case it's quotient filter, and secondary index would help you avoid all the unnecessary IOs, and you would get almost a random read throughput of SSD. We also did some micro benchmark for our file system so that we could compare against ext4 and Fuse ext4. We used Filebench to do this benchmark: sequential read, sequential write, random read, and random write. We used 30 GB file, and IO size was 4 KB. So as you could see, sequential read, all of us get almost a similar performance. And then for sequential write, KFS is around 11% overhead. The stitching actually helped us get closer to ext4 throughput, which an LSM-tree wouldn't have. But we showed that stitching could have some CPU overhead and giving us only like a 10% rather 11% overhead. And then random read, we have 8% overhead. As you could see, Fuse ext4 and KVFS perform similar, and the main overhead comes from Fuse with the memory copies and the context switches. Random writes, KVFS clearly wins, being using underlying LSM-tree nature, so it helps to get better performance for random writes, and we can clearly see KVFS has like 2 times better performance than ext4. So the takeaway from this slide is basically, as you could see, we have KVFS performs comparable to ext4 on all the other workloads, and for random writes, it gets around 2x better performance. We did other benchmarks, which I don't have time to include here. We compared KVDB with that of the LevelDB with benchmarks like random sequential as well as random append. So KVDB performs around 23% faster for small tuples 64 bytes and around 6 times for large tuples for random append workload, and performs similar to that of LevelDB for sequential and random workload. So we also did file system macro benchmarking with file server using Filebench, file server, and web server. When we compare against ext4, file server we performed 22% better than ext4 because of file server being mainly has like a lot of metadata nature in its workload. And web server, we have a 7% overhead when compared to ext4. This again mainly comes from the reads which the web server does and the overhead from Fuse. So we also evaluated our transaction. We show that we used Linux kernel compilation to happen within our transactions, and we show that with a strong serializability mode, we have only 10% overhead, and you could have actually transactions which are non-overlapping in nature and runs parallel. You could get at least 4% faster throughput than running the same thing without transactions. This is basically because each transaction has its own VTTree, so they don't collide with the other transactions to take the log within the VTTree and so on. And then we also evaluated our defragmentation. More details can be found in paper. So in conclusion, we show that in our paper at least that VTTree performs well for all the 4 workloads. And KFS performs comparable or superior to that of ext4 on most of the workloads, including micro and macro. So that kind of we say that it's suitable for desktop and servers. And then we also have low rate transactions and which can be highly concurrent too. And then defragmentation works really well and as a complementary to stitching. So I would like to take any questions now. Thank you.
Peter Desnoyers, Northeastern. There's a lot here to digest, but
I agree.
I do worry when I see someone saying, well, we're going to do cleaning in the background and it's not going to be a problem. But I'm wondering, again, I need to look at this much longer, but have you looked into and seen whether there's any way with the stitching threshold to basically bound the amount of garbage or the rate that it's collected at, so that in fact you can say that cleaning is not going to take over everything, even with workloads you haven't looked at?
Right. So we did try with a lot of other stitching threshold, but the reason is that we have 8 MB zones which we use. We could actually change it to anything, but then we set a stitching threshold to 32 KB or 64 KB because on an average, in a general purpose file system, the average size of the file is 64 KB. So we want to do well for the average sized file. So if you increase the stitching threshold, you end up actually reducing the fragmentation by a lot, but then you do more copies. So that's kind of a trade-off we're trying to look at here. So we could increase it to say 1 MB. That would actually almost remove all the fragmentation. I mean, we have some benchmark which would throw what the distribution of the workload of the data and with the varying stitching threshold, how much fragment it does for the same workload. So it does appear increasing stitching threshold reduces the fragmentation drastically. But at the same time, it defeats the purpose of having it. So we are okay with saving log n copies and then do 1 copy at the defragmentation, which that's what we think, it's okay to do that. Yeah.
Thank you.
Hi.
So I just want to follow up on Peter's question. How is your stitching plus defragmentation different from whole plug-in garbage collection in LFS?
Sorry, I wanted to mention that I forgot I didn't have it in the slide. It is very similar to LFS segment cleaning. The only difference is the way we calculate weight from LFS. LFS does basically depends on the age and the liveness of the data. We look at only the sequentiality of the data and try to calculate the weight on that. Other than that, it is very similar to LFS, yes.
Yeah, so I'd encourage you, I like taking the sequentiality into effect. I'd encourage you to look at the age as well, because I think you'll find that in workloads that turns out to be...
I agree. So the only thing is in LSM-tree, the data is already placed based on their age. The recent data at the top, the older data at the bottom. So that's exactly the reason why we don't really worry about age, because we do it from the bottom. So we first look at the old data and then kind of, yeah. Thank you.